Hi, my name is Sirazus Salekin.
I'm Mansfield.
And I'm Zachary Wells.
We are part of UofSC's Electrical 201 class, and our circuit was Divide and Conquer version 3.0, which is based off of a previous project in our 201 class. Instead of a analog system, we are using a digital system using an Mbed microcontroller. Alright, here we have a completely working circuit which consists of a 12-volt power supply, a Mbed microcontroller which is powered through a laptop, a DC motor that's powered by our 12-volt power supply, and our complete circuit which consists of a LDR, thermistor, 2 buttons, one for start, one for stop, a relay, a transistor, a capacitor, and 2 diodes, and many other resistors. Different ways we control our motor is through this button right here. When you click it, it turns on. And also this button right here, which turns it off. And we also have a photoresistive diode, or the LDR, which turns it on, turn it off, and a thermistor. And we also have a over-torque system, which stops the motor when there's too much torque applied to it.
In this circuit, we have 2 analog inputs to enable the rotation of the motor. One of these inputs is connected to a thermistor. The thermistor changes resistance based on the amount of heat. So we can combine the thermistor in series with a 10 kilo ohm resistor so that we have a sufficiently large difference in voltage drop across the 2 resistors depending on the amount of heat. We can use this change in voltage drop to enable the motor. Similarly, we can use a light-dependent resistor in series with a 2 kilo ohm resistor to get a variable voltage drop that will also allow us to enable the motor, since the light-dependent resistor varies resistance with shade. This circuit also contains 2 manual inputs, one of which is a start button and the other is a stop button. Both of these inputs connect to the Mbed microcontroller as digital signals. So when you press one of the buttons, it sends a digital signal to the microcontroller itself. We also use a digital output from the microcontroller in combination with an analog input to the microcontroller to both turn on the motor and regulate the motor's torque. When the motor needs to be turned on, we send a digital signal from the microcontroller to enable a transistor, which will in turn enable a relay. This relay then allows a 12-volt supply to reach the motor. After the 12-volt supply reaches the motor, if the motor is spinning, the output voltage in current is relatively low. However, when the output current is high, we know the motor is stalling out due to an excess of torque, meaning the voltage at the output of the motor is higher than it should be. We can look at this output voltage using a Zener diode voltage regulator, which we calculated would need a series resistance of about 50 ohms. This output ranges between roughly 0 and 3 volts, so we can read this analog voltage to determine when we want to turn off the motor and view the amount of torque being applied.
This is the program we are using to control the Mbed circuit. Before we can start talking about the code, we'll need to understand what a hardware interrupt is. A hardware interrupt is a function that takes in a digital input, and when that input is either rising or falling, the program stops whatever it's doing and executes a function that's attached to the hardware interrupt. The first thing that we're doing in this program is I defined H and L to 1 and 0 so that we can use simple high and low logic later on. The next thing I did is I declared the hardware interrupts to the digital pins on the Mbed. Note you can't use any other pins on there because it'll give you weird errors. Next, I define the digital output for relay toggle, as well as the analog inputs for our thermistor LDR and our over-torque sensing system. Then I have declared the storage variables for all of our analog inputs. These storage variables are only really necessary if you're using printf statements, because otherwise they don't play nice. Next, these are the ceilings for the analog inputs that allow us to perform a little bit of logic later on. And this is the terminal counter, which basically keeps the terminal from spitting out a bunch of messages that we don't need. The first function that we have here is print status. It prints the status of the relay if it's on or off, as well as the values of all of our analog inputs. It also resets the terminal count to 0 so that we can continue displaying the terminal input. Next, we have our functions on and off. They toggle the relay on or off, as well as prints the status of everything. Next, in our main method, we have the hardware interrupt set and reset attached by the rising edge to our functions on and off, depending on if we want to set and reset the circuit. Next, we have our infinite loop that increments the terminal count, as well as stores our analog inputs into our storage variables. This section right here is the logic that we use to turn the relay on and off according to our analog inputs. If the torque value is greater than or equal to our torque ceiling, and the relay toggle is on, then we turn it off. Else, if the LDR value or the thermistor value are greater than or equal to their respective ceilings, and the relay toggle is off, we turn it on. Then, depending on where the value for terminal count is, we print out the status of everything. If you look on the right, it's been printing out this entire time, and when I turn the circuit on, you'll notice that relay on just printed out, as well as the values for everything. And when I turn it off, it turns off. You can also turn it on using the LDR. And you can stop it using the over torque. And the thermistor also turns it on when it reaches over its threshold. When I can get it to do that. There we go. And it'll turn off as well.